Hi, I'm Mark Perry with Colorado Dam Safety. Welcome back to our tutorial series on our new guidelines for hydrological modeling and flood analysis. This tutorial segment covers Section 5, generating subbasin properties for the CSU SMA modeling method. So the previous tutorial covered getting all the input data. So it's all digital electronic file input data, and in this one we're going to use that data, the DEM, Landsat images, soils data layers, and we're going to generate subbasin properties, all the basin delineation. We're going to use HEC-HMS and our CSU SMA, our toolbox, to calculate subbasin properties. Delineate basins, identify streams and reaches, and soil properties for the subbasins. And then that's Section 5. And then Section 6 is we will use all these properties to estimate parameters for the CSU SMA modeling method. And if you watch the tutorial on the overview, the background and overview of the CSU SMA modeling method, you know there are a lot of parameters in it. So the particularly soil moisture accounting loss method in HMS, but the CSU SMA Python ARC toolbox Python script basically generates all, well, it does generate all of those for us, and so it's meant to be a pretty automated, reproducible, and pretty easy procedure. All right, but first we have to get subbasin properties. Just an overview of this tutorial. The properties we're going to get are, we're going to calculate fractional vegetative cover, raster grid from the Landsat images that we downloaded from the previous tutorial from Section 4 of the guidelines. Then we're going to set up a model in HEC-HMS and delineate subbasins and stream reaches. Next, we'll talk a bit about partial area analysis, partial areas for partial area analysis for use in our REPS rainfall estimation tools, and then we will calculate our subbasin properties, so areas, subbasin characteristics, and reach properties in HEC-HMS. Then finally, we'll go to introduce you to our CSU SMA Python ARC toolbox, which will first calculate basin properties, soil properties, and then it will also calculate the model parameters, but we'll leave that discussion till Section 6 of the guidelines, the next tutorial. And finally, in this Section 5 tutorial, we'll talk about reporting requirements, because we have reporting requirements in the guidelines, and we want to try to, one of the goals of the guidelines is to try to standardize reporting so that every hydrology report doesn't need to be a one-off. So there's just certain things we want to see, and hopefully that will make it easier for engineers and consultants submitting hydrology reports to Colorado Dam Safety for review. Here's Section 5 of the guidelines. And again, if you've been following the tutorials, I'm working off a draft version of the guidelines right now. We expect them to be finalized later this month, but there aren't any significant changes at this point. So we'll get right into it with Section 5.1. Some minor pre-processing of our input data is needed before we actually calculate subbasin properties. So we'll generate from the Landsat images. We'll generate a fractional vegetative cover raster grid, and then we want to just do a little bit of pre-processing on the DEM to simplify analysis in HMS. Then in Section 5.2, we will set up the HEC-HMS model and bring in the DEM, delineate stream network, and then subbasins. We'll talk about partial area analysis if it's needed for REPS analysis based on REPS storm area size limits. And then generate the subbasin characteristics we need for Clarkian hydrograph parameters, reach characteristics we need for Muskingum-Kunj reach routing, and then we'll go through the CSU SMA Python script. We'll run that and generate soil sub-basin soil properties. Okay, and then finally, like I said, section 5.4 here is the reporting requirements. So we'll go over those. All right, so that's guidelines. Let's get right down to business with calculating the fractional vegetative cover from the Landsat images. All right, so here we are back in ArcMap. What you're looking at here is our example basin that we've been using throughout these tutorials here. It's a roughly 235 to 40 square mile basin on the eastern plains north of the on the north side of the Arkansas River here. And I'm showing two different tiles of Landsat remote sensing Landsat images, what they call the B3 band, which is red color band. And you can see here where I left the colors different, so you can see these are two different tiles. The first step we need to do is mosaic those. I covered these in a previous tutorial, but let's just go through it quickly again for people who might not be super familiar with ArcMap. Again, I'll give you the disclaimer that this is not an ArcMap tutorial. It's not intended to be, but we just want to give enough skills that people who might not be familiar with it, so that ArcMap is not a limiting factor in this, using the CSU SMA method. So I'll just try to show you what you need to get through it in ArcMap. All right, and then the goal here is we're gonna do some calculations on these B3 and B4 red and infrared band remote sensing images and calculate a quantity called NDVI, and then from that fractional vegetative cover for the basin. All right, and that's the equations are in the guidelines. I'll show you those, but let's start with mosaicing, or in other words, combining these two different Landsat images. Okay, so we're working with a continuous image here. All right, or continuous raster file here. So we go into data management tools, and this is Arc Toolbox. Going down to data management tools, rasters, and then there's raster data sets and mosaic. So what we need to do is just pick those two and we're going to tile the two B3 images first. Okay, so we have this path 32, row 34, and then the next one is the B3 path 32, row 33. So those are the two images. We'll just pick one of them as the target, and it's just going to combine the other, where I have my input data stored, Landsat images, and I'll just pick the top one, B3 image there, and I'm going to pick for mosaic operator. It's going to choose the maximum. I'm going to just leave that color map as the default. Ignore the background value of 0, and no data value will be 0. Mosaic tolerance is 0, and that will it explains. ArcMap is pretty good about explaining these options in the right side, this right side bar, but that's just going to force resampling if the two grids are offset. Okay, so I'm going to hit OK, and that will take just a minute. So the mosaic operation's done in ArcMap, and so we had these two different tiles. We mosaic those. So let me turn the bottom one, the one that's black and white now, off, and you'll see that they're now combined into a single image. And if you can use the identify tool here and compare those values, and it should have the same values as now in this tile mosaic image as the two previous tiles had. Okay. So anyway, now we have one single raster image of the B3 red Landsat band raster image, and then we'll do the same thing to the B4, which is the near infrared, and then from that we'll calculate NDVI and fractional vegetative cover. And mosaic the B4 Landsat band raster image, and so now we have these two. This is the B3 and then the B4, which are both mosaic and cover the entire drainage basin. Okay, so now from those, we're going to calculate it, like I said, NDVI and fractional vegetative cover. Go back to the guidelines and look at those equations. It's listed out here. They're pretty simple These are standard from scientific literature. CSU used these in their research study, but these are pretty standard. A normalized difference vegetative index, NDVI, it's just this band, B4, B3 band difference divided by the sum, and then we'll take that and calculate the fractional vegetative cover. From that is just the square of a difference from NDVI, and it's just normalized to a NDVI naught for bare soil and NDVI infinity for fully vegetative soil, like a forest cover, something like that. So we'll talk a little bit about how to get those naught and infinity values, and I'll show you how to calculate these equations, these using the raster algebra, the raster calculator in ArcMap. Okay, so let's go back to ArcMap, switch to ArcToolbox, and you do need to have the spatial analyst tool in order to do this. So the raster calculator is under map algebra, and we have raster calculator, but that is under the spatial analyst tool, which is an extension in ArcMap. It's separate license, and you can activate, if you have it and it's not activated or you want to check it, just go to the extensions, and it should, we have it here, I have it here activated. Okay. So with the spatial analyst tool, do this raster calculator, and it's going to give you your choices of rasters. And then a big caveat here is you have to use these operations in the raster calculator. It's tempting to just type things in from the keyboard, but it won't recognize the commands. Okay, so first thing I'm going to do is pick, instead of setting it to the default geodatabase, I'm going to pick a location for my input data. Okay, I've already calculated, so I'll call this NDVI re. That's my output. So I'm naming the output file NDVI. Now, when I come up, this is the equation box. I don't have to type equal. All I do is type the operation that I want the raster calculator to perform on the raster images to calculate this new NDVI raster. Okay, so the first equation from the guidelines was the NDVI equation, float, and that can be found over here on the right in the list of functions. Float puts in parentheses, and I'm just going to do the B4 raster minus the B3 raster divided by the float and then their sum, B4 plus the B3 raster. And I know these are the mosaic images. I actually removed the other Landsat tiles from my ArcMap project so that I wasn't confused by them, but these two here are the mosaic ones that cover the entire basin. So then I just do this raster calculator, and it's going to calculate a new raster, which is NDVI. All right, and NDVI, because just the nature of the calculations, that difference over the sum, it's going to vary between -1 and 1. Okay. I just changed the color band for the NDVI, new NDVI raster that we just calculated. You can see here it varies from about -0.7 to plus 0.59. So next we're going to calculate fractional vegetative cover from this second equation, which is right here in section 5 of the guidelines. So again, it's the NDVI. This I is the grid we just calculated minus these two reference values, basically a normalized range. So infinity is NDVI at fully vegetative cover, naught is NDVI value at bare soil. So you're trying to get that range of values, and then the actual calculated NDVI in compare as a fraction of that full range of NDVI values. Okay, but there's some guidance on that in the guidelines here. Montana and Small recommended determining these values, determining these infinity and NDVI infinity and NDVI not values locally, because they do vary through your Landsat images. what we've seen, some CSU research from CSU found values around 0.04 for NDVI naught to 0.7 NDVI infinity. I guess we've seen similar values of that in the mountains. On the plains here, I'm going to show you that what I've seen is the values are lower. But let's go ahead and jump into that, and I'll show you some different ways to, also the guidelines talk about different ways to do it. So one way we can do it is we could just turn on an image file, and then we can the identify tool here on the ArcMap toolbar, and we can zoom into areas where we can see by the image have good vegetative cover and then bare soil. So if we have good vegetative cover in an area, say an agricultural area, I can do an identify there, and I select, make sure you're identifying from your NDVI layer, and we see there that value is about 0.18. We can, it's going to vary. 0.27 is a value there, up to about 0.28. So remember that value for a possible NDVI infinity. Then let's go to something that looks like bare soil, maybe up in here, and we see a value more around 0.04, 0.05, things like that. So it seems to be. Now, another way we can do this is, and we can go to the Arc Toolbox, back to the Spatial Analyst, and go to reclassify, and it will give us, we can select our NDVI raster, classify it, and ArcMap will give us a histogram showing the distribution of the pixel values, the NDVI pixel values. So let's classify that, and we'll get this histogram, and there we can see the actual range of values. Now remember, this is over the entire, these two tiles of Landsat images that I mosaicked together. So it's a larger area. I think it's still would still qualify as regional values according to Montana and by Montana and Smalls guide recommendations. But if you wanted to get a tighter area, we could always clip that NDVI raster to tighter to the basin. I think we're okay here. Now, by this histogram, you can see, yes, the values do technically go from -0.7 to +0.6, but the bulk of them by far is in this range. And so we look at something like 0.02 up to maybe 0.27. So if we said something conservatively like 0 to 0.3, I think that's probably a pretty good range for our span of NDVI values in this region. So let's go back to the Spatial Analyst tool and the raster calculator. So Spatial Analyst tool, Map Algebra, raster calculator, and we're going to do this second equation from the guidelines to calculate fractional vegetative cover. Stick it here under input data. And call this FG. And the equation is then parentheses float NDVI grid, and this would be minus NDVI naught, which in our case is just 0. So I'm going to get rid of that, and we don't actually need that opening set of parentheses there, because that's for that quantity of our NDVI that we calculated, the NDVI I value minus NDVI naught. So that's just going to be, this is actually a squared quantity, but I've found that it works better just to use multiplication in the raster calculator than to try to square it. But sorry, that's float again, NDVI naught, and then that's going to be divided by the full range, which we said we're using NDVI 0.3 for NDVI infinity, 0 for NDVI naught. So that's just 0.3, and it's that quantity again, that is the denominator squared, so it's 0.3 times 0.3 or 0.09. And again, it's tempting to want to enter that from the keyboard, but don't do it. Just type in using the raster calculator keys here above, keyboard above, use 0.09 there, and that's it. That's our FG calculation. So hit OK. Okay, here's our FG grid, raster grid, the raster calculator calculated from the NDVIs. And this fractional vegetative cover should be between 0 and 1. I mean, it's just a range, the NDVI actual range over this, what supposedly was the maximum range based on our estimates of NDVI infinity and NDVI naught. We're obviously below, or I'm sorry, have some pixel values there, some raster values that are way above 1, but I think this is a good opportunity to talk about a couple of things here. Okay, number one, if this is calculated for this entire mosaic, these 2 raster tiles, so there may be value, the 5-4 values may be way outside of this. They may not even be applicable to our basin, but it does look like there's some high values inside of our basin. Okay, when I can use the identify tool, when I identify those from FG, make sure we have the FG layer selected, and I identify those, they don't seem to be above 1. So one thing I can do is just go back to the spatial analyst, reclassify, and look at the actual distribution of the FG. What I've seen typically in the past is that there's not many. Those are just a few stray pixels here and there. And this, you got to remember, this is going to get average, or you got to realize this is going to get applied to the sub-basin averages, and then used to the vegetative percent vegetative cover, fractional vegetative cover, used to adjust sub-basin average infiltration rates, okay, in the CSU SMA Python script. If we have a few high pixels, it's not going to make any kind of a significant difference, okay? So let's first just see how big of a deal this is by our spatial analyst reclassify tool, and again, we just get that histogram of the actual raster values. Now, it's kind of hard to see. I mean, yeah, it doesn't appear there's many values out here at 5.4. The bulk of them are way down here, well below 1. And one thing we can do here is zoom in on this. And so here we get a better idea of the distribution. Yeah, I mean, most of the values are way way below 1. So I think we're probably, in practical terms, we're probably okay. But it is also a good chance to note that the way the vegetative cover, vegetative adjustment to infiltration rate is done in the in our old guidelines, and then it was applied in the new CSU SMA Python script. It will keep, there's no upper limit to it. So if you actually have FGs, significant FGs at 5.5, it's going to increase your infiltration rates significantly. Just continue to increase them linearly past 1 and up to 5. This vegetative cover of 5, so 500% vegetative cover, it doesn't make sense. It's implausible or impossible. So we don't want, if that really was a significant part of our basin, that's wrong, and you need to recalculate this. But anyway, if it's just a few pixels over a giant basin that's going to get averaged into sub-basin average value, probably not a big deal. So my analysis here, or my assessment here, is this is okay. So, and then the one final note that on FG, and then we're done with it. We've spent probably more time talking about FG than anyone would ever want to. But this footnote we have in section 5 of the guidelines, just people have asked us, people had some in peer review testing, initial testing, this method, people had some problems with it. And they asked us, can't we just calculate this for the whole state? Well, not really, because there is, we talked about in the previous section, input data, section 4 tutorial, there's some site-specific aspects of getting the Landsat images and calculating FG. So just for perspective on this effort, I mentioned it in the previous section 4 tutorial as well. Just we recommend not getting bogged down in this. The FG is simply a starting point. It's a property that's going to be used to adjust infiltration rate, but then later on in this method, we're going to evaluate the results, compare them to the observed flood record, and then we have a chance to calibrate the model. So it's just, there's going to be chance if the infiltration rates come out too high, too low, what have you, then we're going to evaluate the model. We can calibrate it. So this really should just be viewed as a starting point in getting the model parameters. Okay, in terms of guidelines section 5.1 here, pre-processing, just some minor pre-processing of the input data before we calculate sub-basin properties. What we're wanting to do in section 5.1.2 is clip the raster, the geotiff, just so that we're not trying to analyze that entire map terrain DEM in HEC HMS, but really just trying to clip it to at least closer to the size of the basin boundary. Okay, but this is a good case I want to show you. When I bring that DEM into ArcMap and overlay it with my basin boundary shapefile from StreamStats, which, if you recall from the previous tutorial, we said this may not be exactly correct, but it's at least our starting place. The DEM's not big enough, so this tile does not cover the entire drainage area. So we have to do two things. One is go back to the USGS national map and download the adjacent DEM tile. And then second is I'm going to want to come back here to ArcMap and mosaic these two together so that I have a single DEM which I can import into HEC HMS. And our guidelines talk about this. It's useful for for dealing with Landsat rasters and for DEMs. So this is a good place to go ahead and share that. But first, I'm going to jump back to the guidelines, section 4, where we had the link to the national map and DEM terrain. And we're going to go back to my site here, which I'd already zoomed in on in another tab. And I'm going to go back through elevation products, 1/3 arcsecond, and remember to do this search products. We'll see which ones we have here and the thumbnails. And if you remember, kind of zoom out and you see which ones the area is. That's the one I downloaded. Now we need to find this one that's adjacent just to the west of that. So there it is. And I'm going to go ahead and add that to my cart and download that geotiff. Okay, so we downloaded this adjacent DEM tile to the west for our basin from the USGS national map and brought it into ArcMap. So now we have these two adjacent tiles and I want to mosaic them in ArcMap. So in this tutorial is in no way intended to be a GIS or an ArcMap tutorial. We just want to make sure that people maybe aren't familiar with ArcMap or as familiar, have some basic skills they need to facilitate the CSU SMA modeling method and avoid maybe some of the learning curve or frustrations with that. So that's the only intent here. But let's talk about mosaicing raster data sets. So zoom in, we can learn a little bit about the data here. Let's take a look with the identify button in ArcMap and just pick a location on the at the border of these two DEMs. And we can get that value. We have to select which DEM it is. And this one to the left is a 630. So the pixel value right there is about 1486.5. And then if we pick the one to the left for comparison at about the same location, it's 1486.7. So we're pretty close. But as you go up and down this border boundary, you will find that there can be some discontinuities there. So that might inform our mosaicing a little bit. But let's jump to Arc Toolbox. And when you open it, these will all be compressed, and then we're going to drop them go to data management tools, and we're going to go to data management tools, I'm sorry, go to raster, and then raster data set, and in that, mosaic. So as the input rasters, we're going to choose the two DEMs that we have loaded, and then we're just going to pick one of them to act as the target. So this is where the mosaic data, the combined data, is gonna live. The mosaic operator gives several choices here, and ArcMap usually gives descriptions of the options over here in this left column. Because of that discontinuity that can exist at the border between DEMs, what I'm going to do is select blend. In HMS, we're going to want everything to drain, and so we're going to hopefully avoid discontinuities here, where we would have water from the left uphill side not draining, but we're also going to do a procedure in HMS called filling the pits to get rid of any depressions or low spots that don't drain. Okay, ignore background value or no data value, so we're going to leave that ignore background value empty. I'm going to ignore the data value of -99999, and that's the no data value in the DEM. If we jump back to the DEM, you can see that under properties, you can see what the no data value is. Okay, and then mosaic tolerance, I'm going to have as 0, and again, ArcMap explains what that is. So 0 is just going to guarantee, tolerance of 0 is just going to guarantee that there's resampling at the border there if the pixels overlap and don't exactly match the horizontal location. Okay, and that's that, and then I'm going to select OK and hopefully produce a mosaic tile of raster grid of both of these DEMs. So here's when the mosaic is finished, and in ArcMap, this is the original two. These are the original two DEM tiles, and then if I turn off the one to the left, then I get the mosaic tile. And if you remember, I just picked one of the TEFs to be the combined, one of the DEM files to be the combined one. So this is it. So this 630 GeoTIFF DEM is going to be the one that we want to load into HEC-HMS. But before we bring the mosaic DEM into HMS for hydrologic analysis, the guidelines section 5.1.2 talk about clipping it, and that's just to minimize the amount of analysis that HMS has to do. We don't need to analyze an entire DEM mosaic for drainage patterns. We just want to concentrate on our basin area. But remember, we said this may not be the exact, the StreamStats basin shapefile may not be exact, or may not be what we want to use exactly. So I'm going to first do a little bit of a buffer on that, just to preserve a little bit of a DEM buffer in the DEM around the StreamStats basin shapefile. So we'll go into analysis tools, proximity, and buffer, and just pick that global watershed, the StreamStats drainage area shapefile, and this is just going to go to the default geodatabase. That's fine, and I'm just going to give it some offset. A couple thousand meters should be fine, just to preserve some of the DEM there. So let's just call it 2,500 meters there, and everything else I'm just going to use the defaults and go with that. Okay, this red boundary is our buffered drainage area shapefile. So let's just do a quick clip of the DEM before we bring it into HEC-HMS. So under Arc Toolbox, drop-down data management tools, raster processing, and clip. And we want to clip this mosaic to DEM. If you remember, we put that into the 630 geotiff. Our clip extents are going to be based on this global watershed buffer. The warning here is just it's in a different coordinate system, but ArcMap's smart enough to figure that out. So we'll select to use the input feature for the clipping geometry, and I want to change the location. And importantly, so this is in my project file on my C drive, and I'm going to just name that clip DEM. But importantly, I'm going to keep that TIFF file extension so that it'll stay in geotiff format, and our HEC HMS will recognize it when we bring it in. Okay, so we're going to save that, and no data value is good. We're going to hit OK, and ArcMap will clip the DEM to that red basin boundary buffer. Now we're ready to go into HMS and go ahead and use HMS to determine subbasin properties. So we're in the Hydrology Guidelines paragraphs, or section 5.2. Let's go to HMS. I'm using version 4.10. As we said in previous tutorials, this, HMS versions change frequently for everyone who knows HMS. So far, we've not seen any significant changes that affect the guidelines. All right, so I created a new project in my project file, and the first thing I'm going to do is go into the components, and I'm going to create the basin model manager, create a new basin, and I'm just going to give that my dam name or reservoir name. So create that. So we have the basin model, and then the next thing we're going to do is go back to components and create the terrain. So this is a new terrain file. I'm just going to leave that default name, terrain 1, and I'm going to go looking for that clipped, mosaic clipped DEM that we just made. So I'm going to go to my C drive where I'm keeping all my, and there we have it. And it is this TIFF file, clip DEM TIFF. Select that. The units are in meters, and that came from USGS where we downloaded it. And I'm going to go with finish. There. Now I'm going to go back to the basin model, and I'm going to link that basin model to my terrain model. And I'm going to set the coordinate system. I'm going to use predefined UTMs. And for most of Colorado, except the very western edge, we're in zone 13, northern hemisphere, NAD 83 datum. So select that, set it. There we go. Okay, and there we have it with our clipped, our mosaic clipped DEM in HMS. Continuing with our subbasin properties analysis in HEC HMS, we created an HMS model, a basin model, and then a terrain model. We brought in our mosaic and clipped DEM as a terrain, and we linked it to the basin model. So now we're ready. Well, and we also set a coordinate system. Now we're ready to analyze the drainage network in HMS from the DEM. And that takes us to a little bit of a tricky part, is subbasin area size and subbasin delineation. So I want to try to simplify that. This is an area of this the CSU SMA modeling process that requires some judgment. So there are several considerations when we're looking at subbasin area size, and then we're going to have to consider those when we delineate subbasins in HMS. HMS asks for a drainage network area threshold, which is where it starts, the contributing area where it starts a stream for the drain as part of the drainage network, and then that's going to inform. If you leave HMS to its own devices, that's where it's going to inform where it puts subbasins, because they're going to be at the junctions of that drainage network. So the denser the drainage network, the more subbasins you're going to have. But then we can also we can put in breakpoints to manually set subbasins when HMS delineates it. So before we do that, let me talk about the various considerations. Okay, so let's jump to a PowerPoint slide. I'm going to try to simplify this. All right, so subbasin area size considerations. Number one is actually goes back to our section 4 and our section 4 tutorial for the design rainfall. So there are two considerations for REPS design rainfalls. One is REPS climate regions. There are several climate regions in the state where there's going to be major differences in rainfall from one to the other. And in those cases, we need to, the guidelines recommend dividing the basin and running those different subbasins for those different climate regions in REPS. The next REPS consideration is actually the storm area size. So section 4 of the hydrology modeling guidelines lists the REPS area size limits. They're also in all the REPS documentation as well. But if you have, if your basin exceeds the REPS storm area size limits, then we're going to be into what we call partial area analysis, where you're only using part of the area, most likely the lowest area and the area closest to the reservoir, to run in REPS and get the design storms for a partial area analysis. Okay. The next subbasin area size consideration is CSU's from their mountain hydrology research study. They used an subbasin area size of 15 square kilometers, which equates to about 5.77 square miles. Now, the reason they did that was it was a variance study of spatial patterns of the historic storms rainfall that they used for the calibrating, developing the model and calibrating it to these historic observed floods in the Front Range, so 2013, 1976, and a 1997 storm. Now, we don't necessarily have to follow that because we're generally doing design storm analysis, and our design storms don't have that same spatial pattern variation. However, what CSU found when they did their verification study is they tried to run it both ways. Their model, once they had developed the model and the parameter estimation methods, they ran it with this area size, subbasin area size limit. But then when they tried to eliminate subbasins and just run entire basins, they found that they generally got lower peak flow. So they did not get the same results. So the feeling was that baked into the parameter estimation methods is something about that area size limit. So we kind of need to follow at least somewhat close to that area size limit. However, in these guidelines, we have the additional step of later on of the reasonableness checks, the checks against the observed flood record, and then calibration. So even if we used larger area sizes and our in the model, the CSU SMA model produced lower peak flows, we have a chance to go back and check it against the observed flood record and a chance to calibrate it. So it would be a matter of using the smaller subbasins on the front end, maybe a little bit more data entry and input into HMS versus larger subbasins, and then having to check it and calibrate it to the observed flood record on the back end. Okay, the last consideration would be physiographic differences, and like climate regions, these are going to be major differences of a basin. So the example would be a basin dam on the eastern plains, where the basin started up in the mountains and then passed down through the foothills and to the plains. So the mountains, foothills, plains are significantly different physiographically. We'll have different loss rates, different unit hydrographs, and so those kind of differences for sure need to be separated out into subbasins. Okay, so let's look at the REPS transposition regions. You can get those. You have the REPS. If you have the REPS PMP tool, you can find the storm transposition zones where you have your PMP evaluation tool, and then it's under input, and there's a non-storm data geodatabase. When you go into that, you'll find a shapefile called transposition zones. Just load that, and I have the colors changed around and labeled by zone. But you can see here zones 1 and 3. In this case, here we show they're the eastern plains and the foothills region, and then 5 gets up into the mountains. So this basin that we've been using as our example basin does not really, there's not much difference between these plains and foothills regions as far as rainfall. What we see, this boundary between zones 3 and 5 is the roughly the 7,500 foot boundary that has a significant difference in rainfall and flooding. So let's go to another example basin, and in this case, let's change the color so we can see it a little bit better. In this case, the basin crosses from this foothills high intensity rainfall region to the mountains, and even up into the sheltered mountains that are have significantly lower rainfall, lower PMP, lower precip frequency. So in this case, we would want to have subbasins at least delineated for these separate REPS regions, and then run those in the REPS tools and get separate, the REPS PMP tool, and get separate PMP estimates for this region and for the Zone 3 region and the Zone 5, 17 region. The reservoir and dam is here. Now, the second bullet I showed is that partial area size analysis. So if this basin also exceeded the REP storm area sizes, then we may also be looking at just doing the analysis based on a part of this basin area, partial area analysis. And generally what we'd be looking at is this partial area that's lower, closer to the reservoir, and in this higher rainfall, intense rainfall region, REPS transposition zone. Okay. Lastly, let's go to HMS and look at the procedure then for processing the drainage area network and delineating subbasins. So this is all in the GIS menu or drop-down menu. We already defined the coordinate system. We would pre-process sinks, which I've already done. That just fills pits in the DEM, and I talked about that being potentially an issue when we mosaic the 2 DEMs along that boundary. I ran that, it fills the pits. Now that's something that the user or the engineer has to make a judgment call about. There may be pits that are real or depressions, certain topographies that you don't want filled, but HMS is going to fill, but if you run this, it's going to fill any pits or sinks so that the entire topography drains. Then we run pre-process drainage. It computes a drainage accumulation raster, and lastly, we're going to identify streams. And when we do that, HMS is going to ask us for this area threshold. So what I did was the CSU, again, the CSU research study used this area size of 15 square kilometers or 5.77 square miles. I told you we're not necessarily beholden to that because that was based on spatial variation of historic rainfall patterns. but we also don't want to stray too far from it because the parameter estimation methods were developed by CSU using this area, subbasin area size, and they found it somewhat dependent on that. We do have we have our process for reasonableness checks and calibration where we can mitigate that somewhat. But I'd like to tell you to stick to around 10 square miles if possible, or 10 square miles or less. So I used a 10 square mile area threshold in HMS, and it delineated the drainage network. Okay, so then we can select our pointer, go back to our subbasin map, and turn on and off map layers. So I'm going to just show it's showing all of everything it did: the sink fill, sink locations, the flow direction, accumulation grids that it did in the pre-processing. I'm going to turn all of those off and show you the stream network that HMS delineated. Turn off the terrain. Okay, so here it is. This is the stream going down to our reservoir and several branches there. Now, the next thing that we're going to do is put in breakpoints. We're going to import the stream stats. So we're under map layers, add, and we're going to import the stream stats going back to our project file. The stream stats point of concentration that we downloaded earlier. And then we can zoom in on that, and we're going to put a breakpoint there and use that as our point of concentration. We can put additional breakpoints in to manually define subbasins, or if we just run the delineation in HMS, it's going to define subbasins where there are junctions for in the drainage network. So if we want to use reps to inform where we put the reps transposition zones to inform where we put subbasin breakpoints, then we can import that reps storm transposition zone shapefile into HMS. So I did that. I had to load it from the geodatabase in ArcMap and then export it from the geodatabase as a shapefile. It's just fairly simple. Just from here, just do data and export as a shapefile. Then HMS can't recognize the geodatabase, but it will bring in a shapefile. So I loaded that, and we can turn that on, and that would show us where these basin boundaries are. So this was that boundary. Zoom out here a little bit. That was that boundary between zones 1 and 3. So if we had our basin that crossed, say, from zones 3 to 5, we can see that here. We could put it, compare it to our stream network and put a breakpoint for a subbasin at that boundary where we want to run the separate, get separate reps rainfalls for the different climate transposition zones or climate zones. Okay, so I'm going to turn that map layer, the reps transposition map layer, off because we're not using it in this case, since this basin is on the eastern plains, foothills region. It's a fairly homogeneous climate region. What we do need to do in this test case is the partial area analysis. So if you recall from my slide, PowerPoint slide, we had the 4 drainage area size considerations. So the first one was reps climate zones. We just said we don't need that here on the eastern plains. But then the second bullet, second consideration, was reps partial area analysis. And that goes back to section 4.6 of the our new guidelines for hydrological modeling, flood analysis. Now you could also reference the reps tools guidelines, which are on our website, or you can reference the original reps summary reports from the study. But what we're looking for is the reps storm area size limits. Now, this example basin we're doing on the Eastern Plains, the drainage area is 249 square miles, according to stream stats. Like we said, this basin may not be exactly right, but it's our starting point. So by the REPS storm area size limits, that exceeds the area size of the REPS PMP 2 and 6 hour local storm PMP, the guidelines. Like we said before, the tool will still run, but it's recommended to limit that to 100 square miles. Okay. 24-hour, we don't know until we run the tool and see what the historic controlling storms are and see what's kind of size limit. But I'm gonna say probably 100 to 200 square miles. We don't need to worry about the general storm. There's no size limit. Now, when we do REPS Met Portal precip frequency, we're in this East Macker region for our reservoir and the drainage area on the Eastern Plains. We have a 200 square mile size limit for local storms, so we need to be aware of that. We need to have a 200 square mile partial area. 6 hour, 500 square miles, we're less than that. We don't need to worry. And 48-hour MLC, again, like the big synoptic scale storms, 1,000 square miles, we don't need to worry about that. We're less than that. Okay, so it looks like for REPS partial storm, small storm, simple convective thunderstorm, partial area analysis, we need partial areas, subbasins for partial area analysis that are 100 square miles for PMP and 200 square miles for the precip frequency. Okay, so the way we're going to do that is to let HMS delineate subbasins, and then based on the area threshold of 10 square miles we gave it, and then we'll just sum those up, combine those to form our partial 100 square mile, 200 square mile partial areas. So I changed we have the stream network that HMS identified. I changed the color to make it more visible. So it's these blue and green lines, and if we zoom in here, we imported our stream stats point of concentration, the global watershed point shape file, and then we created a breakpoint at the directly on the stream network near to the stream stats point of concentration, and then we went into GIS and did delineate elements. And so what what HMS does at that point is it uses its stream network and the area threshold we gave it. It used the area threshold to delineate this stream network, identify streams, and now it goes in and creates subbasins at the junctions. Now, if we needed subbasins at specific points, like say a stream gauge for our stream gauge analysis, our reasonableness checks, and basin or model calibration later on, we could create another breakpoint and put it at the exact stream gauge location, or like we said, at a REPS climate zone boundary or some other physiographic feature if we wanted to control exactly where those subbasins were, where a subbasin division was. In this case, I'm not so worried about that. So we just let HMS do it based on its stream network. And then these are the subbasins and subbasin areas we ended up with. And I just threw those into Excel, and it looks like roughly what we have is going up through subbasin 8. We'll have about 100 square mile if we consolidate all of those for REPS rainfall purposes up through subbasin 8. So that's this lower portion of the basin. That will be about 100 square miles. So what I'm going to do, and then this upper portion, I'm going to take these subbasins 1, 3, and 14, and those are another 100 square miles. So that will give us our 200 square mile partial area, and then we'll leave off this subbasin 2, which is the last 50 or so square miles of the entire drainage area. So we'll have two partial areas, and I'll export this subbasin. We'll go ahead and do that now. Export this subbasin shapefile and then import it into ArcMap, and I'll just dissolve those different subbasins and create two partial areas. One is this lower 100 square miles, and then the other one will be this larger 200 square miles, and then we'll be able to use those partial area shape files in the reps, this lower one in the reps PMP tool for the local storm analysis, and then this larger 200 square mile partial area in the reps Met Portal precip frequency tool for the local storm analysis. Now, I want to make a couple points. One is want you to appreciate that this is a complicated test case or example case. So I could just show you, if you have a simple basin that's 10 square miles, whatever, you're going to have a single basin. You're not going to have any probably reps boundaries in it. You're not going to have any partial area analysis, and this is going to be a very simple process of delineating the drainage area and then moving on, calculating basin properties. This is, I wanted to show you, but then you would get to this more complicated case and have no idea what to do. So in this example case, I'm giving you about the most complicated it can be, and then hopefully you'll be happy if you have a simpler case. So let's go ahead and export the subbasin file. So that's under GIS. We're just going to export layers. The subbasins is what we want to export, and we're just going to put it in our on our C drive where we have our input data. Okay, so I'm going to call that HMS subs as HP, and there we'll have that, which we can import into ArcMap. And then I want to show you, while we're here, we're calculating basin properties in HMS. So we have the subbasin areas. Those are here. We can copy and paste those into Excel in a few minutes and or a little later for our reporting purposes. Again, up to the parameters drop-down menu, we can calculate more basin properties, characteristics, subbasins, and I already did these, but we can recompute them. And this is going to give us our basin properties that we'll use in a spreadsheet to calculate Clark unit hydrograph properties. And then lastly, we can get our reach characteristics. So these are our reaches, and we will run those and use these properties just to do our Muskingum-Kunj reach routing in our HMS model here. So now we brought the HEC-HMS subbasin shapefile into ArcMap just for processing, and what the point here is for this partial area analysis to facilitate our reps rainfall analysis. So we want to consolidate these lower basins, about 100 square miles of them, lower subbasins for the reps PMP local storm, and then all these upper basin, the whole thing except really for this far upper left basin to get the 200 square mile partial area that's corresponds to the size limit for the reps precip frequency analysis, local storm 2-hour local storm precip frequency analysis. So again, these tutorials are not meant to be ArcMap tutorials. We just want to show enough that people, if you're not super familiar with GIS, you have enough skills to get through this, so that that's not, ArcMap's not an impediment to people using the CSU SMA method. Okay, so here we have this purple file, fuchsia, the HMS subbasin file. You can go in and select the subbasins that we need, and a shift select lets you pick air control, lets you pick various ones of them, and then with that X'd out, you can simply export those data, selecting on the layer, then data export, and then those can go to a shapefile, a new shapefile, which you can import in. I've already done that. and that was this file. Now it comes in still with the individual subbasins. We don't want that for reps analysis. Generally, let me explain that a little more. But generally what we're just looking for is this 100 square mile or 200 square mile, whatever it is, partial area boundary. Okay. So what I do next is I take that extracted shapefile of the lower subbasins, go to our toolbox, and I dissolve that, and all that does is get rid of these internal boundaries. So that's under, data management. This is always the trick in ArcMap, right, is finding where the tool, there's a tool to do everything, but it's finding it is the trick. So data management tools, generalization, and dissolve. Okay, so we just pick this this extracted PMP local storm partial area analysis shapefile. Don't select any of this, just go ahead and hit OK. And again, I've already done that for the sake of time, so we'll go back to our layers, table of contents, and here was the dissolved one. Now, you notice it had the HMS subbasins had some few weird funky lines in here, and I then went in and cleaned it up, which you may have to do. The other reason I want to show this is because if your if you don't agree with your HMS delineated subbasin, or say a StreamStat subbasin, you can bring it into ArcMap and manually edit it. So we go up to the editor. You can add that through your toolbars, start editing, pick the file that we want, so this dissolved file, and then at that point we can just edit vertices, and what I did was selected all those vertices with a backward window, selected those, and then deleted vertices. But you can move vertices, insert vertices, delete vertices, and basically clean up your subbasin, in this case our partial area analysis shapefile. Okay, now as far as the point I wanted to make about what we want whether we want individual subbasins for using in reps, that's kind of a case by case. In general, or in this case, I guess, for our example basin, all I'm looking for is that a partial area of that lower 100 square miles, which I'm going to use in reps. Now I'm going to get a consistent a uniform reps rainfall estimate across this entire area. And I'm going to apply that rainfall uniformly as a single stream or precip gauge to all these subbasins in HMS. There may be other times reps PMP tool will do an actual subbasin analysis. So if you put this subbasin shapefile, it will calculate from gridded raster PMP data. It will calculate a separate PMP estimate for each of these subbasins, which you could put in as a separate stream gauge, precip gauge in HMS for each of these. That would be, a more advanced analysis if you have reason to think that you want more of a distributed model. The main case we talked about would be where you cross that reps climate region and you had two main areas, a lower one in one climate region, an upper one in another. Then you would want a basin shapefile with two subbasins or two regions defined in the shapefile, and then reps will return separate PMP estimates for each subbasin, which you would preserve and enter into HMS as separate precip gauges. This is our second partial area for the around 200 square mile one for the Met Portal reps precip frequency analysis for the 2-hour local storms. So corresponding to that 200 square mile size limit. Now that's in the reps, the Met Portal precip frequency tool, like I explained earlier. Those area size limits are strict limits. So this partial area has to be less than 200 square miles, or the Met Portal will not return that watershed estimate for the 2-hour local storm precip frequency estimate. So we want to check that. You can just do a quick check of that area. So if we just if we just add a field here and let's do a long integer and do area square miles. Okay, and then we're just going to calculate that geometry, ignore that warning, and do this in square miles. And we can see there that it's 195 square miles. Our partial area, the subbasins that we extracted to form this 200 square mile partial area, is 195. That's good. It's close to 200 square miles, but it has to be less, or MEP portal precip will not return a watershed precip frequency estimate for that storm type, the 2 hour. In this case, the 2 hour local storm is the one that has the size limit, area size limit that we have to be worried about. Okay, before we move on from all the subbasin delineation stuff and do the final step of calculating the soil properties introduce you to the CSU SMA Python ARC toolbox, we need to create that tool. The CSU SMA Python script needs a raster version of the HMS subbasin or basin file, shape file. So we're going to do this in the guidelines here, section 5, 5.2. We've gone through this process of delineating the subbasins in HMS. We exported them using the export GIS menu, export georeferenced elements, and now finally we're going to go import that. We did import this HMS shapefile, or I did, into ArcMap. So just going to do a quick conversion, super simple, but just conversion tools to raster, and then polygon to raster. Okay, so you just pick the HMS subs and put it where you want to. The default size comes up, and just run that. I already did that. Takes a minute. The ArcMap stuff always takes a while to process, so I just already did it. And what it comes up as is this: it assigns unique values to each of those subbasin elements. So I think not sure it's essential. In fact, it's probably not, but I'm just going to go ahead and reclassify that just to make it simpler. So I'm going to go, we've talked about this tool before, but the spatial analyst tool, reclassify that. I'm going to pick this input raster and the subs raster, and all I'm going to do is change those unique subbasin property values all to 1, and I won't put you through that, but I'm going to end up with a raster that's all just 1s, and then no data will be no data outside of that. Okay, so you just need that, and then next step we're going to proceed to the CSU SMA, introduce you to the CSU SMA Python script, ARC toolbox, and how to calculate the soil property. All right, the last set of properties that we want to calculate here in section 5 of our hydrology guidelines is the subbasin average soil properties. And we're going to go ahead and I'm going to go ahead and introduce you to the CSU SMA Python script, ARC toolbox. Okay. Now, I'm not going to go into details. I'd prefer to introduce it in detail in the following section where we actually talk about the model parameter estimation. But the tool does, as a first step, calculate these subbasin average soil properties, percent subbasin, percent sand, clay, organic matter, depth to restrictive layer, and fractional subbasin average fractional vegetation cover based on those grids that we have developed to this so far. We got this, if you watch the previous tutorials, we downloaded the NRCSG NATSCO raster data with sand, clay, organic matter, depth to restrictive layer in section 4, the section 4 tutorial, and then the Landsat images, and then in this tutorial here, section 5, we just calculated fractional vegetative cover raster grid. Okay, so it's the CSU SMA tool is going to calculate subbasin averages. Then in the next section 6, it's going to use those for model parameters. So let me just do the most basic introduction to the tool. If we flip to section 6, download the CSU SMA tool here, and we have it on a Google Drive. So if we click this link in section 6.2, you're going to go to one of our dam safety Google Drives, and what you'll need to do is snag both of these, the TBX file, toolbox file, and the loss folder, and then just download those. Okay, now put those on. I would recommend you put those on your local C drive, and then go to ArcMap, go to Arc Toolbox, and add a toolbox. Okay, navigate to where you put the CSU SMA toolbox on your local C drive, and simply add that. Okay, and it comes in. It should be ready to go. You may have to check properties about where the location is of the TBX file, and then here's the actual script. If you look at properties of that, that tells this path tells the toolbox where the Python script code is. It should be smart enough to know that it's relative to where you put the Python tool, but if it's not, you may have to redirect this folder, the source path location, to find it wherever you put the Python script on your computer. All right, so I'm going to cancel that, and then to run, we just double click on that script. Okay, now before we do, what we're going to need to load is sand, clay, organic matter, depth restrictive layer raster, our fractional vegetative cover raster, our subbasin shapefile from HMS, and then the subbasin raster that we just created. We're going to give it an output folder location. Again, we're going to pick our local C drive. So before we do that, let's actually load those soil layers that we downloaded from our dam safety FTP, DNR FTP in the section 4 tutorial. I recommended just putting those at a general place on a local C drive, because those are going to be used over and over. It covers the whole state, so you'll use those for any project you do here. Okay, so we're going to let's just start with depth restrictive layer and add all 4 of those GNATSCO raster files that cover the whole state. So there's % clay, here's % organic matter, and finally we'll do % sand. Okay, so everything should be here. We have our HMS subbasin file, and we have our fractional vegetative cover raster grid. Lastly, we should have our subbasin, HMS subbasin raster version. That's here, subs raster 2. So going back to the SMA, CSU SMA, Python Arc Toolbox. Now let's just navigate. Those will appear as layers in our current project. So % sand raster, % clay raster, % organic raster, depth to restrictive layer raster, fractional vegetative cover, and we have that right here. We made it. Subbasin shapefile. This is a shapefile. It's going to ask us to go looking for that. So that is in my project file, my input data, my HMS subs, and then we have our subbasin raster that we did the conversion, the polygon to raster conversion on. So it's subs raster 2, and the output folder, I'm going to get out of input data now, and in my project folder, I'm going to create an output, CSU SMA output folder. And I'm going to run the CSU SMA Python script arc tool. It's executing, and it tells a little bit of information about what it's doing. And it succeeded. We're finished. We can close it. Now, go back to our project. navigate to the output folder we created, and all of the Python script, CSU, SMA, Python, our toolbox output is in this folder now. So what we want, all we want at this point in section 5 is this sub-basin average soil properties. So I'm going to go ahead and load those tables: clay, depth restrictive layer, FG, organic matter, and sand. The rest of these are all soil hydraulic properties and HEC HMS model parameters, which we'll talk about in the next section, tutorial section 6. So I add these sub-basin soil properties, and we can open those, look at them, and we can export them for use. Okay, so what it gives is your sub-basins. We have 16. It gives the column we generate. It gives the zonal statistics on each of these properties. What we are interested in is this mean value. That's our best estimate. So in other words, percent here, sub-basin, percent clay, sub-basin average, percent clay. Sub-basin 1 has about 12% clay. Sub-basin 2, 17%. Sub-basin 3, 37%, etc. Depth to restrictive layer. Okay. Gives our units here, means, and now the output of these is in inches. Sub-basin soil properties, depth to restrictive layer, fractional vegetative cover, the mean column. So those are in decimal fraction, and organic matter here, and it looks like I missed the percent sand, so let's go back and snag that. Clay. Okay, there it is. Open that. And this is our column again, mean column, percent sand. Okay, so those the sub-basin. That's it for as far as sub-basin soil properties from the CSU SMA Python ARC toolbox. Okay, last but not least, in section 5, let's talk about the beginnings of our reporting requirements. And as I said before, we took the opportunity in these guidelines to try to standardize hydrology reporting for Colorado Dam Safety Review, so that every study or every report does not need to be a one-off effort. So hopefully that will make things easier for consulting engineers submitting reports for our review. So section 5.4, and we do this, if you recall from an earlier, I think section 4 tutorial, we went through the table of contents and section 3, and noted that that where you see this red heading and the paper scroll, these throughout the document, these indicate reporting requirements. So just call those out. Why did we put them embedded throughout the report? Because it kind of works in a linear procedure. What we say here for this tip, if you do the reporting along the way, number one, I think it's easier. There's less back and forth. So as you're calculating these things, as you're doing GIS analysis, just go ahead. So in this section, doing GIS analysis for the sub-basin properties, just go ahead and print the attribute tables instead of finishing the entire analysis, then having to go back, reopen everything and print. So print it as you go. Tells you what you need as you go, section by section, and what we're looking for. And then also, it does help to have, I think, some of this printed out, the tables, the maps, to facilitate the analysis. So it's kind of a cumulative process, or built on itself, of having the properties, reviewing those, and then generating model parameters, having those spreadsheets set up, property summaries, tables, parameter summary tables, and then building the model. So that's the way we do it. Section 5.4 is the subbasin properties reporting requirements. There's an Appendix A that shows an example of these reporting requirements, of all the reporting requirements in the document here, in the guidelines. Okay, so let me go through these quickly and show you some of the spreadsheet tools that we have that just even should make this very easy and standardized. And then I'll go through example Appendix A quickly and show you what the reporting requirements looks like for properties. All right, so section 5.4.1, first thing would be REPS PMP tool. Output, we're looking for GIS maps, cumulative rainfall, showing spatial patterns for all relevant storms. So if there's 2-hour local storm, 6-hour local storm, and then for the Front Range, there will be 24-hour local storm as well, and then 72-hour general storm, and if 72-hour tropical storms applicable, then that as well. Print basin average, attribute tables, we talked about that just shows the average PMP for each time duration, each storm type. Print temporal distributions, we have a spreadsheet tool for that. So just we talked about the REPS PMP tool, the temporal pattern, temporal distribution attribute tables in GIS, export those, and then we made a spreadsheet where you can just copy paste those into spreadsheet worksheets, Excel worksheets, and that you'll have a height graph plot up on that. So, and then this is displaying in Google Sheets, but it's actually an Excel file. So download it. And it will look different. The recommendation would be here to download it and then use it in Microsoft actually do the editing Microsoft Excel. Okay, next, then the PMP points file. That's that GIS attribute table from the REPS PMP tool that shows each controlling storm at each grid point of your basin for each PMP duration. Okay. Next, REPS Met Portal precip frequency output. I talked about this when I was demonstrating the Met Portal tool, but we want to see a screenshot of the precip frequency curve table with confidence bounds, PMP plotted for comparison, and then showing the map, just a screenshot showing the map with your basin imported, so we can verify what basin's being used for each analysis, each storm type. And then print the temporal distribution image, and the temporal distribution data that you download. Okay. Then if there is partial area analysis, which we went through thoroughly, if your basin exceeds REPS storm area size limits, then we need to document that with a sample. We have a sample spreadsheet tool, but clearly document which subbasins are used. Okay, so which subbasins are used for which storm type, storm duration. So for here we have 19 subbasins. It's a total of a 207 square mile basin, so it exceeds some of the REPS limits, and this was on the west slope, so it exceeded some of the REPS storm area size limits. So 2-hour, 6-hour local storm PMP, we only use these subbasins. 24-hour storms not applicable. For general storm, used all of those, and then similarly for the Met Portal precip frequency, etc. So partial area now document which subbasins are used for each storm partial area analysis. Okay, document what values used for NDVI not and NDVI infinity. Okay, in order to come up with calculate your fractional vegetative cover raster. Then print the CSU SMA Python subbasin property output tables, which we just went through. So show us the actual output from the Python script that shows that mean column, the subbasin zonal statistics, but specifically that mean column for percent sand, clay, organic matter, depth restrictive layer, and then fractional vegetative cover. Show us print the subbasin properties table, and this will combine the output, the subbasin output from the CSU SMA Python script on soil properties, depth restricted layer vegetation, and the properties, the subbasin characteristics from HEC-HMS. Let me jump to that. We talked about this, but if you go to parameters, you'll need to grab subbasin areas. That's the first table under parameters. So you grab your subbasin areas. Then next one down is subbasin characteristics. That has longest flow path, slope, centroidal, length, etc. And those all have a place in this sample spreadsheet tool. Again, an Excel spreadsheet that we've created for you, just as an easy subbasins property table to show the things that we're looking for. So this first part, again here, the left columns are from the CSU SMA Python script. You just copy and paste those from each attribute table, the GIS attribute table that you export, and then from, again, exporting from the HEC-HMS characteristics subbasins table and subbasin area table and subbasins characteristics table. Just put those subbasin areas and those basin characteristics. Okay, so that's that. And then the same thing for stream reach, that comes from HMS. That was the next table under parameters, characteristics, the reach table. And that just gives the properties that you'll need for doing reach routing in HMS. So we want to see those summarized as a check. Again, okay. So it's another sample spreadsheet. This is very simple, just to show us those reach properties. For each reach exported from HEC-HMS. Okay, and then lastly, in section 548, we're looking for some maps from the GIS to show good spatial patterns and visuals of these various properties. So subbasin delineation, and the subbasins labeled with aerial imagery and topo map, and then maps of the rasters for sand, clay, organic matter, and restrictive layer vegetative cover. And then this last section 549, we just say that the user needs to do QC checking, and that the first step would be this properties point section after section 5, just to make sure all the subbasin properties look consistent, look reasonable in comparison with all the different inputs and your maps and what HMS is telling you, and whether they all make physical sense for the basin and the region of interest. Okay, so let's jump back to this example output reporting in section A, and that will just take you to the Google Drive appendix, and you can open one of those. There's two examples here for the appendix A reporting, and then we're just looking here at the reps storm data and the subbasins property. So I'll go through this quickly. Again, spatial maps for reps PMP, the different storm types, the hydrographs of the temporal distributions for each storm type, then just the basin average PMP, attribute tables from GIS for each relevant storm type. Zoom in on this, and this is the GIS or the reps PMP storm or points attribute table that tells the controlling storm types for each duration at each grid point. That's extremely helpful to us for reviewing. And that's here, like local storm here, and then general storm PMP. Here are the temporal distributions for from the reps PMP tool for 2-hour, stack distribution 6-hour, synthetic east distribution, and that's a long one. And then one of these should be the 72-hour distribution, general storm distribution also. Okay, then we jump to Met Portal. We're looking for the screenshot, precip frequency table, graph, confidence bounds, PMP overlaid, and then a screenshot with the map showing the basin that you used. And the 3 different storm types, 2-hour local storm, 6-hour MEC, and 48-hour MLC. The temporal patterns, images from the Met Portal tool, and then the output data for the temporal distribution scaled to each ARI or AEP. And I just deleted, I'm using accumulated precip in my HEC HMS model, so I deleted the incremental columns to just show one column for each ARI. 3 storm types, local storm, MEC, and then for MLC. All right, subbasin properties summary. This is that subbasin property summary table where you have the example spreadsheet, then reach parameters, and the output attribute tables from the Python CSU SMA Python script, percent sand, clay, organic matter. And this just helps us check that everything came out of the tools, entered correctly, and then fractional vegetative cover. Then the maps, so subbasin map overlaid with topography, and then aerial imagery, the sands map, clay map, organic layer, depth restrictive layer, vegetative cover, and that's it for the subbasin properties reporting. All right, so that's the end of section 5. We now have subbasin properties, and we're ready to proceed to section 6, using the CSU SMA Python script to actually calculate all the HEC HMS model parameters for us. So join us for the next tutorial for that. Thank you.